Welcome to Looping Pixels. Today we are going to explore inside the universe's most extreme prisons. Just take a moment and think about that idea. Ultimate cosmic isolation. I mean, what actually happens to you, or, the information that makes you you if you fall into one of these places?
Places where the rules of physics we rely on are, well, they're pushed to the absolute limit, stretched, squashed, maybe even broken entirely.
We are, of course, talking about black holes, the universe's sort of ultimate isolation chambers.
Yeah.
Really the most extreme prisons imaginable.
Exactly. And exploring them forces us really to confront what we actually know and maybe what we don't know about reality itself. These aren't just objects out there. They're like these cosmic laboratories.
Right, where gravity is king and quantum mechanics just struggles.
It really does.
So our mission today really is to get inside these concepts. We're going to look at the boundaries, the structure inside, at least theoretically, and the, frankly, bizarre physics that happen there. And we're sticking purely to the sources we've gathered for this.
Yeah, we're starting right at that edge, the event horizon, the point of no return. And we'll journey inwards, theoretically speaking, towards the core of spinning black holes, where the math suggests things get incredibly weird, things that challenge our basic ideas about time.
It sounds like a journey into physics at its most extreme, all right.
Right.
Okay, let's start with that wall, the prison wall itself, the event horizon. It's probably the most famous part of a black hole, right? We see it in all the pictures. But what is it, physically?
Fundamentally, it's the boundary where escape velocity, the speed you need to get away, becomes faster than the speed of light.
Okay, so light can't get out, meaning nothing can.
Precisely. Since light speed is the universe's speed limit, if light is trapped, everything else is too.
So it's not like the light just slows down and gives up.
No, that's a really important point in general relativity. It's better to think of it as space-time itself. The fabric of reality is flowing into the black hole towards the center, faster than light speed at the horizon.
Wow. So light is still moving at light speed locally?
Locally, yes, relative to the space right around it. But that space is dragging it inwards relentlessly, like being on a super fast conveyor belt heading towards a cliff.
Okay, conveyor belt to oblivion. Got it.
Yeah.
Now let's picture ourselves watching this happen. We're safely outside, watching, say, a probe fall in. What do we see? Because gravity messes everything up, right?
Yeah, it absolutely does. For us, the outside observer, the big effect is gravitational redshift. As the light from that falling probe tries to climb out of the black hole's immense gravity, well, it uses up energy.
And losing energy means?
If wavelength gets stretched, it shifts towards the red end of the spectrum, hence redshift. It gets dimmer, redder, weaker.
Does it ever actually cross the horizon from our perspective?
Well, this is the weird part. The light takes longer and longer to reach us. The time dilation becomes extreme. So the time it would take for us to see it actually disappear completely, it stretches out towards infinity.
Infinity, you mean it just hangs there?
Effectively, yes. From our viewpoint, it would take longer than the current age of the universe for it to truly vanish. So the probe, or the poor astronaut, appears to slow down, get dimmer and redder, and essentially freeze, just hovering right above the event horizon, forever fading.
Like a ghost image stuck on the edge of reality.
Okay, but that's our view, distorted by time dilation. What about the probe itself? What does the traveler experience crossing that line?
Right, switch perspective. According to Einstein's general relativity, the theory that's been incredibly successful, predicting gravitational waves and all that, the crossing itself is, well, nothing special.
Nothing special. Crossing into a black hole.
Physically,
Yeah.
at that exact moment, yeah. The theory says you just glide smoothly through the horizon. No signpost, no bump, no sudden jolt. You just cross this invisible mathematical line.
And suddenly you're cut off, forever.
Suddenly and irrevocably cut off from the rest of the universe.
Yeah.
Never getting out. That sounds almost peaceful, which is terrifying, given where you're headed.
Yeah.
A smooth slide into oblivion. But that classical picture, that smooth glide, that's exactly where modern physics starts to freak out a bit, right?
That's putting it mildly. This is precisely where general relativity crashes head-on with quantum mechanics. It leads to something called the information paradox.
Yes, the information paradox. Can you unpack that a bit? Why is the smooth horizon such a problem?
Okay, so very basically, general relativity suggests that when something falls into a black hole and hits the singularity at the center, all the information about what it was like, was it a cat or a computer, is completely destroyed, gone forever.
Okay, sounds nothing.
But quantum mechanics has this fundamental rule called unitarity. It insists information can never be truly destroyed. It can be scrambled, hidden, transformed, but the universe always keeps track, somewhere.
So black holes seem to break quantum mechanics.
That's the paradox. If information goes in and vanishes forever, quantum mechanics is wrong. And then Stephen Hawking added another layer with Hawking radiation, the idea that black holes slowly evaporate over eons.
Right, they leak energy.
Exactly. So if the black hole completely evaporates and the information inside is gone, well, where did it go? If it's truly gone, quantum mechanics is violated. If quantum mechanics holds true, the information must get out somehow, maybe encoded in that Hawking radiation.
In trying to figure out how it gets out, or if it's preserved, that leads away from the smooth glide.
Precisely. This struggle led physicists, particularly around the early 2010s, to propose something really radical: the firewall.
Okay, firewall, that doesn't sound smooth or gentle at all.
Not even remotely. The firewall theory suggests the event horizon isn't empty space you glide through. Instead, it's a hugely dense radiation bath of photons, basically. A wall of incredibly high-energy particles.
A literal wall of fire at the edge of the black hole.
That's the idea. Anything attempting to cross the event horizon hits this firewall and is instantly incinerated, annihilated.
Whoa, so the information doesn't get lost inside because it never truly makes it inside. It gets, like, burned onto the outgoing radiation.
So that's one way to think about it, yeah. It solves the information paradox by basically destroying whatever falls in right at the boundary, but it completely contradicts the gentle glide predicted by general relativity.
So the event horizon goes from being an invisible point of no return to maybe the most violently destructive place in the cosmos.
Potentially, yes. And the frankly embarrassing thing for physics right now, as some of our sources put it, is that we genuinely don't know which picture is correct. Is it the smooth crossing Einstein described, or is it this quantum inferno?
That's incredible. We're actually starting to see these boundaries with telescopes, where we fundamentally disagree on what happens when you touch them.
It really highlights the need for a deeper theory, something that unifies gravity and quantum mechanics, a theory of quantum gravity. We have these two amazing rule books, GR for the big stuff, QM for the small stuff, but at the black hole's edge, they give totally opposite answers. Glide in or burn up? Still a massive question mark.
Okay, so whether the entry is smooth or fiery, once you're past that horizon, or maybe as you approach it in the firewall scenario, your physical form has a date with destiny. And that destiny has a great name: Spaghettification.
It really is a disturbingly perfect name, isn't it? Spaghettification describes the destructive effect of the black hole's tidal forces.
Tidal forces. We know those from Earth's oceans, caused by the moon. That's pretty gentle. How does it become spaghettification?
It's the same principle, just ramped up to unimaginable levels. A tidal force isn't about the overall strength of gravity. It's about the difference in gravity across an object.
Right. The moon pulls slightly harder on the side of Earth closer to it.
Exactly. That difference stretches the Earth, causing the ocean tides. Now, imagine falling towards a black hole. The gravity increases incredibly rapidly as you get closer.
So the difference in pull between, say, your head and your feet becomes enormous.
Enormous and growing exponentially. The strength of the tidal force depends on the mass of the black hole. But crucially, it falls off with the cube of the distance. So as you get closer, that differential pull skyrockets.
Okay, paint the picture. I'm falling in feet first. What happens?
Two things happen simultaneously, and they get worse fast. First, stretching. The gravity pulling on your feet is significantly, massively stronger than the gravity pulling on your head. This difference stretches you vertically along the direction of the fall.
Like pulling taffy.
Exactly like pulling taffy. That's the spaghetti part. But at the same time, there's a second force: squeezing.
The squeezing? How?
Gravity pulls everything towards the central point, the singularity. So the gravitational forces acting on your shoulders or your sides aren't perfectly parallel. They're converging towards that single point. This pulls your sides inward while you're being stretched lengthwise.
So you're being stretched vertically and crushed horizontally at the same time. That's unpleasant.
Deeply unpleasant. And it doesn't stop at the microscopic level. This process continues down to smaller and smaller scales as you plummet towards the singularity, that theoretical point of infinite density.
Where physics breaks down anyway.
Right. The tidal forces become strong enough to rip apart the molecules holding you together, then the atoms themselves, and eventually even the fundamental particles that make up those atoms. Everything gets shredded.
Okay, that's a terrifying theoretical fate.
Yeah.
But we actually see this happening out there in space, don't we? These tidal disruption events.
We do. TDEs are basically spaghettification happening on a stellar scale. When an unlucky star wanders too close to a supermassive black hole, usually at the center of a galaxy.
The black hole's tidal forces just rip it apart.
If they overcome the star's own gravity holding it together, yes. The star gets stretched and torn into long streams of gas.
And we see this from Earth.
We see a huge flare of light. As the star gets shredded, some of that stellar material gets flung outwards, but a lot of it falls towards the black hole, forming a swirling, superheated disk called an accretion disk. The friction and compression in this disk generate intense heat and light X-rays, UV, visible light, that can outshine the entire host galaxy for months.
That sounds incredibly violent. Our sources mentioned a specific one, studied by UC Berkeley researchers back in 2019.
Ah, yes, that was a really interesting one. It was relatively close, astronomically speaking, in a galaxy in the Andromeda constellation. A star about the size of our sun got torn apart by a supermassive black hole.
And what was special about it?
Well, for one, it was bright enough to study across many different wavelengths of light, which gave a lot of detail. But the really surprising thing, the mystery, was what happened to the stellar debris.
What do you mean? Didn't it just fall in?
Well, that's what simple models would suggest. Once gravity grabs it, it should mostly spiral inwards. But in this 2019 event, a lot of the material, maybe even most of it, was ejected away from the black hole at high speeds, blasted back out into space.
Huh. How does that happen, if gravity is pulling it in?
That's the puzzle. Simple gravity alone doesn't explain these powerful outflows. The leading ideas involve other physics coming into play. Maybe powerful magnetic fields generated in that swirling, disrupted plasma.
Magnetic fields. How would they eject material?
As the stellar gas gets compressed and heated, it can generate intense magnetic fields. These fields can then act like channels or jets, maybe aligned with the black hole spin axis, and funnel a significant chunk of that material outwards before it gets swallowed. Relativistic effects near the horizon could also play a role.
So spaghettification isn't just stretching, it's this complex mess of gravity, magnetism, and superfast plasma.
Exactly. Events like that 2019 TDE show us it's a much more dynamic and frankly messy process than just a simple gravitational shredding. There's a lot going on.
Okay, so far we've mostly talked about the simplest kind of black hole, when defined just by its mass, the Schwarzschild black hole. But realistically, most things in the universe spin, right? So black holes probably spin too.
Oh, absolutely. Real black holes are expected to have not just mass, but also angular momentum spin, and maybe some electric charge, though that's usually thought to be negligible. When you add spin, you move from the Schwarzschild model to the Kerr model, named after Roy Kerr.
And adding spin changes everything.
It fundamentally changes the geometry inside the event horizon. It introduces new features, new boundaries, and a key effect called frame dragging.
Frame dragging. That sounds intriguing. What is it?
It's one of the wildest predictions of general relativity. Imagine the spinning black hole is like a heavy ball spinning in a vat of thick honey. As it spins, it literally drags the honey, the space-time around with it.
So space itself is swirling around the black hole.
Exactly. Close to the spinning black hole, space-time is being dragged around so intensely that nothing can stay still relative to the distant universe. Even if you try to hover, the swirling space forces you to rotate along with the black hole.
Okay, so if our poor traveler falls into a spinning black hole, they're not just falling straight down, they're being dragged around in this cosmic whirlpool.
Yes, and falling inward rapidly. But the rotation adds another layer of complexity. As you fall deeper, the effects of that rotation, the centrifugal force, become more significant relative to the inward pull of gravity.
And this leads to another boundary inside.
It does. Inside the event horizon of a spinning black hole, there's theoretically a second critical boundary called the inner horizon, or sometimes the Cauchy horizon.
Inner horizon. Okay. What happens there?
This is where things get really, really extreme. The inner horizon is basically where the outward push from the intense rotation, the sort of centrifugal effect on space-time itself, balances the inward pull, briefly slowing the inward flow of space back down to the speed of light.
And our sources called this place the most violent place in our universe. Why so violent?
Because it's a region of incredible instability and energy convergence. Imagine everything that has ever fallen into the black hole throughout its history, plus radiation trying to get out. It all effectively gets amplified and focused near this inner horizon.
Amplified how?
As particles approach this boundary, they get blue shifted to incredibly high energies. You have particles that fell in billions of years ago colliding with particles falling in now, all interacting at near light speed within this highly warped, chaotic region. The energy densities become enormous.
Like a particle accelerator, but
yeah,
cosmic and terrifying.
far beyond any accelerator we could build. It's described as a chaotic cosmic blender where particles slam into anything falling through with energies potentially high enough. Well, high enough to match the conditions right after the Big Bang.
Wait, the Big Bang, are you saying?
This is where it gets highly speculative, but yes. The energy concentrations calculated for the inner horizon are theoretically comparable to those needed to initiate something like a Big Bang.
So the inside of a spinning black hole might be a place where new universes are born.
It's a mind-bending idea, isn't it, that the endpoint of gravitational collapse, this ultimate prison, could also be a site of cosmic reproduction. If baby universes can form anywhere, the inner horizons of curved black holes are considered a prime candidate location according to the mathematics.
That's staggering. Okay, but the weirdness doesn't stop at the inner horizon, does it? The math predicts even stranger stuff deeper inside.
If you mathematically follow the Kerr geometry past the inner horizon, things get even more bizarre, possibly unphysical. One prediction is that this deep interior region could have a negative total mass energy.
Negative mass energy. What does that even mean? Like anti-gravity?
It's related to how physicists define the total mass of a system by looking at space-time far away, the ADM mass. The calculations for the deep Kerr interior suggest this value becomes negative. Physically, negative mass is doubly problematic. It usually implies instability in physics we just don't understand. It's often taken as a sign that the classical GR description is breaking down completely there.
And there's something even stranger related to time travel.
Yes. Perhaps the most famous and troubling prediction for the region beyond the inner horizon is the possibility of closed time-like curves, or CTCs.
Closed time-like curves. Paths through space-time that loop back on themselves.
Exactly. These are theoretical pathways where, if you followed one, you could travel through space-time and end up back at an earlier point in your own history. You could, in theory, meet your past self.
Time travel, the ultimate paradox generator.
Precisely. The existence of CTCs means causality breaks down effects could precede their causes. The inner horizon, the Cauchy horizon, acts as the boundary. Before it, causality seems to hold. According to the math, past it, you enter this region where time loops become possible. Most physicists think this indicates a failure of general relativity in this extreme regime, that some quantum gravity effect must prevent these paradoxes. But it shows just how strange the predicted interior of a spinning black hole really is, not just physically violent, but potentially shattering our fundamental notions of time and cause and effect. Hashtag V gravity, time, and the black hole's influence.
Okay, let's pull back a bit. We've established the black hole as this ultimate prison. Nothing gets out past the event horizon because you'd need to go faster than light. But then, how does the black hole's gravity get out? If gravity travels at the speed of light too, shouldn't it also be trapped inside? How does it still pull on stars and galaxies outside?
That's a classic question, and it highlights a key aspect of general relativity. We need to stop thinking of gravity as something the black hole sends out, like a signal.
Okay, so what is it then?
In Einstein's theory, gravity is the curvature of space-time. When the star collapsed to form the black hole, it warped the space-time around it. That curvature, that gravitational field, already exists outside the event horizon.
So the field was established before the horizon formed, or as it forms.
Exactly. The outside universe isn't interacting directly with the singularity hidden deep inside. It's interacting with the curved space-time locally, right where the stars and galaxies are. That curvature pattern persists even after the mass that created it is hidden behind the horizon. The field has its own independent existence, in a sense.
So the gravity we feel outside is like an echo or a fossil of the mass that's now trapped.
That's a decent analogy. Also, defining precisely where the black hole's mass is located is tricky in GR, because the gravitational field itself contains energy, and energy equals mass. You could argue the mass isn't just at the singularity. To get the total mass, you have to integrate the field's effects out to infinity. So, in a way, the mass's influence is already everywhere, in the form of that space-time curvature. It doesn't need to escape the horizon because its effect is already present outside.
Okay, that makes sense. Let's talk about time again. We said the outside observer sees the falling object freeze at the horizon. You mentioned time dilation. Can you explain geometrically why time slows down near massive objects?
Right, it's purely about the geometry of space-time. Think of space-time as a flexible fabric. Massive objects create deep dips or wells in this fabric. Now, time isn't separate from space, they're interwoven. Right. And just like spatial distance can be warped, the distance in the time direction can also be warped by gravity. Physicists use something called basis vectors, like little rulers, to measure intervals in space and time. Near a massive object like a black hole, the basis vector for time literally gets shorter.
The ruler for measuring time shrinks. How does that make time appear slower to someone far away?
Okay, this is the key part. There's a rule in relativity that the total length of an object's path through space-time, it's 4-vector, must look the same to all observers. It's invariant. So if the unit of time measurement, the basis vector, gets shorter near the black hole for the falling observer,
Then the amount of time measured, the number of ticks on their clock, has to get larger to keep the total path length the same.
exactly. To compensate for the shorter time ruler, the time coordinate component for that observer has to increase relative to a distant observer whose time ruler isn't shrunk. So while the falling person feels time passing normally for them, that's their proper time.
We, far away, see their clock ticking incredibly slowly, our coordinate time view, because their time coordinate has stretched out enormously due to the compressed time ruler near the black hole.
You've got it. It's a purely geometric effect of gravity warping the measurement of time itself. Different observers, different local geometries, different views of time passing.
It's mind-bending. Okay, now for another twist. Thermodynamics. Heat, disorder, entropy. What on earth does that have to do with black holes, these super cold, information-destroying objects?
It seems completely unrelated at first, right? But the connection came from thinking about what happens to information. When stuff falls into a black hole, it seems like the details are lost. All the black hole remembers is mass, spin, and charge.
Everything else is just gone.
That's what it looked like. This apparent loss of information, this increase in hidden or unknown details, sounded suspiciously like entropy in thermodynamics, which is also a measure of disorder or lost information.
Interesting parallel. Was there a specific discovery that cemented this link?
Yes, the breakthrough was Stephen Hawking's area theorem in 1971. Using general relativity, he proved mathematically that the total surface area of a black hole's event horizon can never decrease over time. It can only stay the same or increase, for example, when two black holes merge.
Never decrease.
Yeah.
Just like entropy in a closed system never decreases according to the second law of thermodynamics.
Exactly. The parallel was too strong to ignore. Physicist Jacob Bekenstein then proposed that a black hole's entropy must be directly proportional to the area of its event horizon. This is the Bekenstein-Hawking entropy. It even led to the Bekenstein bound, the idea that the maximum information you can pack into any region of space is determined by the area of its boundary, and black holes basically hit that limit. They are maxed out on entropy.
Wow. Okay, but if black holes have entropy, like a hot object, thermodynamics says they should also have a temperature and radiate energy. But they're black. Nothing escapes.
That was the contradiction. And Hawking resolved it in 1974 by bringing quantum mechanics into the picture. He showed that due to quantum effects right near the edge of the event horizon specifically, the creation and annihilation of virtual particle pairs in the vacuum.
The quantum foam stuff.
Kind of, yes. One particle of a pair might fall in while the other escapes, carrying energy away. This means black holes aren't perfectly black. They should emit a faint thermal glow, like a perfect black body radiator. This is Hawking radiation.
So the prison wall leaks thanks to quantum weirdness.
Yeah.
What determines how hot this radiation is?
It's inversely proportional to the black hole's mass. This is crucial. Tiny black holes are incredibly hot and radiate intensely. Massive black holes, like the ones formed from stars, are extremely cold, colder than the background temperature of the universe.
And this radiation means they lose mass and eventually disappear.
That's the prediction. They slowly evaporate. But the timescales are just astronomical. For a typical stellar mass black hole, maybe 10 times the sun's mass, it would take something like 10 years to evaporate completely.
$10 years. That's
Yeah.
basically forever compared to the age of the universe.
Pretty much. Only hypothetical, much smaller primordial black holes could have evaporated by now. But the principle stands: black holes aren't eternal prisons. They do eventually dissolve.
It's amazing we can even calculate that.
Yeah.
But even more amazing is that the area theorem, the idea that the horizon area never decreases, has actually been observed.
Yes, this is where things get really cool, connecting deep theory to real data. In 2021, scientists confirmed the area theorem using gravitational waves.
How you can't exactly measure a black hole's surface area with a tape measure from light years away.
No, but you can use the gravitational waves emitted when two black holes collide and merge. They analyzed the signal GW150912, the very first black hole merger detected by LIGO back in 2015.
What do they look for in the signal?
By analyzing the waveform, the chirp of the gravitational waves, they could figure out the mass and spin of the two original black holes before they merged, and the mass and spin of the final single black hole after the merger. From mass and spin, you can calculate the event horizon area using formulas from general relativity.
Man, did the area increase?
It did. They found that the area of the final black hole's horizon was indeed greater than the sum of the areas of the two initial horizons, just as Hawking's theorem predicted decades earlier.
That's incredible. Seeing a fundamental law about black hole thermodynamics confirmed by ripples in spacetime from a cosmic collision. That's a perfect example for looping pixels, connecting the theoretical loops to the observed pixels.
Beautifully put. It's a real triumph for physics.
So gravitational waves confirm black holes exist and merge. But then came the Event Horizon Telescope, the EHT, which actually let us see them, or at least their silhouette.
An absolutely amazing achievement. The EHT basically links radio telescopes across the globe to create a virtual telescope the size of Earth. This resolution is finally sharp enough to see the region around supermassive black holes.
And they imaged two famous ones, right? M87 and our own Milky Way's SGRA.
That's right, M87 first in 2019 and Sagittarius A, SGRA star in 2022. What you see isn't the black hole itself, but its shadow, the dark patch, where light is captured surrounded by this bright ring of glowing hot gas swirling just outside the event horizon.
Now, the images look kind of similar, a fuzzy orange donut. But the black holes themselves are vastly different sizes, aren't they?
Oh, hugely different. M87 is a monster, about 6.5 billion times the mass of our sun. SGRA is much smaller, relatively speaking, only about 4 million solar masses.
So why do their shadows look roughly the same size in the sky?
It's just a cosmic coincidence. M87 is enormous, but very far away, about 55 million light years. SGRA is much smaller, but it's right in the center of our own galaxy, only about 27,000 light years away. The difference in size and distance cancels out, making their apparent size on the sky very similar.
Lucky for us.
Yeah.
But imaging SGRA was much harder, took longer to achieve. Why was our own black hole more difficult to photograph?
The main challenge was its variability. SGRA is much smaller than M87, which means the gas orbiting it moves much faster.
How fast are we talking?
The gas near the event horizon whips around in a matter of minutes, not days or weeks like M87. This means the appearance of the SGRA, the shape and brightness of that glowing ring, changes significantly even during a single night of observation. They call it intra-hour variability.
So it's like trying to take a long exposure photo of something that's rapidly changing shape and brightness.
Yeah.
A cosmic blur.
Exactly. And remember, the EHT isn't one giant dish. It's a sparse network of telescopes. Imagine trying to solve a jigsaw puzzle where most of the pieces are missing, and the picture on the pieces keeps changing while you're trying to put it together.
Okay, yeah, that sounds incredibly difficult. How did they even reconstruct an image from that?
It took incredibly sophisticated computer algorithms and years of work. They had to develop new techniques to account for the rapid changes in the sparse data, essentially finding the image that best fit the data while also being consistent with what we expect a black hole to look like based on general relativity.
And the final image they got for SGRA, that glowing ring. You mentioned its shape, told us something important.
Yes, the fact that it looks like a fairly symmetric closed ring is significant. The appearance depends quite a bit on how the black hole is oriented relative to us. If we were looking at it edge-on, or if its spin axis was pointed right at us, relativistic effects would make one side of the ring appear much brighter than the other, more like a crescent.
But it's pretty even all around.
Right. The symmetry suggests we're likely viewing SGRA more face-on, or at least tilted less than about 30 degrees relative to our line of sight. That helps constrain models of the black hole and its environment.
Fascinating. Okay, we've talked about the black holes we see, made from stars or lurking in galaxy centers. What about the ones we don't see? The hypothetical ones from the dawn of time, primordial black holes.
PBHs. Yes, these are purely theoretical at this point, but a really intriguing possibility. The idea is that in the ultra-dense, chaotic conditions of the very early universe, fractions of a second after the Big Bang, some regions might have collapsed directly into black holes without needing a star first.
And because they didn't come from stars, they could be any size.
Potentially, yes. Their formation mechanism doesn't have the same mass limits as stellar collapse, so PDHs could theoretically range from incredibly tiny, maybe the mass of a large mountain compressed smaller than an atom, 10 or 12 kilograms, all the way up to thousands or even millions of solar masses. Some could even be microscopic, with masses around 10 kilograms, Planck relics.
But wait, didn't we say black holes evaporate via Hawking radiation? Wouldn't the really small ones have disappeared by now?
Exactly. That's the key constraint. Hawking radiation is stronger for smaller black holes. Calculations show that any PBH formed with a mass less than about 10-12 kilograms, roughly the mass of a large asteroid, would have already evaporated completely over the 13.8 billion years since the Big Bang.
So only the asteroid mass ones or heavier could still be around.
That's the idea. A PBH with a mass of, say, 10 kilograms would have a lifetime of only about 2.6 billion years, much less than the age of the universe. So it would be long gone.
And what happens at the very end of that evaporation? You mentioned it's explosive.
Very. As the black hole shrinks, its temperature skyrockets and the radiation becomes more and more intense. The final fraction of a second is a runaway process, releasing a huge burst of high-energy particles and gamma rays.
How huge?
The energy released in that final burst from an evaporating PBH today would be comparable to a hydrogen bomb yielding millions of megatons. A truly enormous explosion from something initially microscopic.
Wow. Are astronomers looking for these final bursts?
They are. Telescopes like the Fermi Gamma Ray Space Telescope constantly scan the sky, looking for unexplained bursts of high-energy radiation that might match the signature of an evaporating PBH.
Have they found any convincing signals?
Not yet, unfortunately. No confirmed detections so far. But the search continues, and PBHs are still very interesting for another reason. They're considered a possible candidate for dark matter.
The invisible stuff that makes up most of the universe's mass.
Exactly. If there were enough PBHs out there, perhaps in the asteroid mass range or heavier, they could potentially account for the missing mass we observe gravitationally without interacting with light. Future telescopes and gravitational wave detectors might be able to spot them through other effects, like gravitational lensing. They remain elusive, these potential unseen prisoners. #tag7 outro.
Well, this has been quite the journey into the universe's most extreme prisons. We started at the event horizon, that ultimate wall of isolation, where we found this fundamental clash between a smooth crossing and a potential quantum firewall.
Yeah, a real puzzle. Then we saw how gravity turns destructive with spaghettification, literally shredding stars. But even that process is more complex than we thought, with things like magnetic fields playing a big role.
And diving deeper into rotating black holes, we found the inner horizon, this incredibly violent place, maybe even a nursery for new universes. And beyond that, regions where the math predicts anti-mass and even time travel loops that break causality.
It's truly physics on the edge. But we also saw how these prisons are tied to fundamental laws. The area theorem, confirmed by gravitational waves, shows even black hole boundaries obey rules similar to entropy, the law of increasing disorder.
We've glimpsed their shadows with the EHT, considered the possibility of ancient primordial ones still lurking. Yet the theories point to interiors where our basic understanding of time, mass, and cause and effect just seems to fall apart.
Which really brings us to a final, kind of unsettling thought to leave you with. If the inside of a spinning black hole truly holds energies like the Big Bang, and if its geometry mathematically allows for paths that violate causality, those closed time-like curves, well, how much does the stability and the orderly progression of our universe depend on these incredibly chaotic interiors remaining hidden, remaining prisons, fundamentally inaccessible to us?
That is definitely something to mull over. A universe potentially dependent on keeping its most extreme places locked away. Well, if this exploration into extreme physics has captured your imagination and you appreciate analysis drawn straight from the sources, make sure you subscribe to Looping Pixels for more.
Thanks for joining us.
Join us next time as we explore the surprising history and science behind T's a future topic.